All right, welcome to the International Methods Colloquium. I'm Justin Essery, an associate professor of politics and international affairs here at Wake Forest University. The IMC is a periodic, online, interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Wake Forest University and previously sponsored by Rice University and the National Science Foundation. The IMC is affiliated with the Society for Political Methodology, who hopes that you will support quantitative research in political science by joining. The membership fee is just $10 a year for graduate students. I will post a link to join the Society in the Zoom webinar chat window just after this introduction. This week's speaker is David Carlson from Koc University in Turkey. His talk is entitled Estimating a Counter-Factual with Uncertainty Through Gaussian Process Projection. Gaussian process projection being an unintended theme of the IMC in the last few weeks. David's talk will last between 30 to 40 minutes, after which point we will take questions from the audience. You can ask a question at any time using the Zoom Q&A button that appears at the bottom of your webinar window, but we will hold all questions until the end of the talk, unless it's a very, very brief clarifying question. A link to David's paper and slideshow will be available in the Zoom webinar chat window so that you may refer to it throughout the presentation, and I will post those links right after this introduction. Now I'd like to welcome David Carlson to the IMC. David, welcome.
All right, great. Thank you, Justin, for having me, and thank you, everyone, for being on the other end of this. So as Justin mentioned, the title of my talk is Estimating a Counterfactual with Uncertainty Through Gaussian Process Projection. Just in a nutshell, to give you a little preview, it's basically a more generalized Bayesian non-parametric alternative to the synthetic control method, which we'll get into shortly. So the overview of the talk, I'm going to talk about Gaussian process regression for time series cross-sectional analyses, which is some work I've done previously that's unrelated to this paper, but I think will help motivate the Gaussian process projection. And then I'm going to specify the GPP, Gaussian process projection, with the identity link. And then I'm going to replicate the application in the original synthetic control method paper, which looks at the effect of West German or Germany reunification on West German GDP. I'll then apply it to a novel application looking at capital flight in the United Kingdom after the Brexit vote. And then I'm going to generalize the GPP in two ways. The first is to allow for multiple treated units at different times. And I'll use as a motivating example the effect of joining the EU on financial stability. And then I also generalize it to allow for link functions. Specifically, I'll demonstrate how to generalize it to a negative binomial link and look at terror attacks by Afghan nationals following the US intervention in Afghanistan in late 2001. I'll then finish with some concluding remarks about some drawbacks of the model and some future directions, etc. So Gaussian process regression for time series cross-sectional analyses. Each point or outcome in a Gaussian process is a draw from a separate normal distribution. So you can think of a Gaussian process as a distribution over function space, where each outcome is coming from a different function. But it's a little bit, the fact that they're all normal distributions makes it a little bit more intuitive, because this can be represented, the collection of points can be represented by a multivariate normal. And the variance covariance of that multivariate normal is kind of where the trick comes into Gaussian processes. We're going to smooth over the covariate space for Gaussian process regression. And by this, I mean points that are closer in the covariate space, so closer in the hyperplane. In the prior, we'll share more correlation. And as those points move further away from each other, the outcomes will be less correlated in the prior. And the degree of correlation is learned from the data. So Gaussian processes are typically used for machine learning. I'm applying them for inferences for political science, but the degree of correlation is not assumed, but instead learned from the data, which is a nice feature of the model. And the correlation that I'll be dealing with is just over time within and across units. So in my applications, these units are countries, but they can be anything. They could be survey respondents on a panel survey, for example, or municipalities or states or whatever. So here's a plot of Gaussian process regression. Again, we're not at the Gaussian process projection point yet. This is from my earlier work. And there's the only inputs to this model are an indicator for the country. So these are 4 Latin American countries, and a continuous time variable. And what you see is that GPR allows correlated but different time trends across units. You also see that the function is relatively smooth, and also where there exists no points. So Venezuela 2007, there's no data point there. GPR gives a reasonable estimation of what that data point likely would have been, importantly with uncertainty. Right? And so moving on to how we would apply this to Gaussian process projection, what we're basically going to do is imagine that Venezuela was treated at time 2008. We would drop all of the values after that treatment, and then basically use the same modeling technique to predict counterfactual covariates and also predict the counterfactual outcome, and then compare the counterfactual outcome to the actual outcome with these uncertainty estimates, allowing us to determine how unlikely the differences are due to chance. So moving on to Gaussian process projection, we're going to predict the counterfactual covariates. So the covariates after treatment are dropped, and we predict them. And similarly, we'll predict counterfactual outcome variables. And then we simply compare the counterfactual to the actual outcome, so that we can make inferences as to the treatment effect. And as I'll get into a little bit later in the talk, this treatment effect is not an immediate treatment effect. It is able to capture treatment effects in the immediate, the short term, the medium term, the long term, which is a nice feature of the model. We're going to model the explanatory variables and missing explanatory variables. So both post-treatment explanatory variables and just data that happens to be missing, with random effects and a Gaussian process. And we're going to model the counterfactual outcome similarly. And then a really nice feature of this model is because I model the unknown covariates jointly with the unknown outcome, the uncertainty from the imputation of the unknown covariates carries over into the uncertainty in the outcome. And I'll specify these in more detail in a few slides. But for the applications, I use a stationary kernel for the explanatory variable. The kernel is basically the function that estimates the variance covariance prior, and then a non-stationary kernel for the outcome. This is just due to the features of the data in my applications. This can be changed by the researcher depending on the data features of the specific application they're interested in. So the explanatory variable specification, let T index time, I index unit, which just as an example can be country. Gamma is going to be a time random effect. Lambda is a unit random effect. And then eta is this GP term, which I'll get into more detail in a couple of slides. So this X TI is superscripted with a star because some of this is missing and some of it is not, but these are modeled jointly, both the missing variables and the observed variables. And it's just going to take a normal distribution with a common intercept, the 2 random effects, and this GP term with a variance sigma sub x. So Notice there's no covariates that go into this. If I were to, it's possible to include covariates, but again, because we're dealing with post-treatment variables, we would basically have to impute those and it would just become sort of a nest. And so I decided to just model this based on the temporal trends in the GP and the random effects, plus the common intercept. The outcome variable specification, again, let T index time, I index unit, gamma be a time random effect, lambda a unit random effect, and eta the GP term. So I'm superscripting these by Y. If you notice back here, superscripted these by X because I'm using the same gamma and lambda for these time and unit random effects, but they're obviously not the same parameters that go into the X modeling as they are that go into the Y modeling. So I superscript them by Y. And then for the applications, this eta, this GP term is non-stationary. And so again, Y star here, because some are missing and some are not, are going to be jointly modeled normally very similarly to the explanatory variable with these random effects on the GP term and common intercept, but now we also have this X star times beta, which is the covariates that some are missing and some are not, hence the star superscript, and then multiplied by some estimated parameter beta. So GPs have a tendency to overfit and to avoid overfitting and get appropriate coverage. So with the 0.95 posterior, we want to capture 0.95 points, which I do with placebo tests, which I'll get into later on in the talk. But basically all I do is take the final prediction, Y hat, and distribute it normally centered at this Y star with this noise level psi. And as I said, I'll discuss how to determine that value of psi later in the talk. So the Gaussian kernel, also known as the separable exponential kernel, is a stationary kernel. We use that for the explanatory variables. And the variance covariance is estimated from the data. So we have this, imagine a column of covariates, one covariate, a column vector X star, because there's some missingness in it. We're going to distribute that multivariate normally with the mean function Z beta and variance covariance sigma squared times omega. And as I said, I don't actually put covariates into the mean function, but the Z beta is just more of a general notation for this particular kernel. In the mean function, I'm just putting in random effects for time and unit and a common intercept. So the trick is in estimating this omega, or specifying the prior on the omega. And so we start by defining it as between units j and units I. We take the exponential of the negative sum of the squared distances across dimensions. So here P is indexing dimensions that are going into the estimation, and M is the total number of dimensions. We're just taking the difference, squaring them, and summing it. And so points that are very close together will have a prior correlation very close to 1, and points that are further away will have a prior correlation closer to 0. But we want to allow different dimensions to have different levels of correlation or degrees of correlation. So we introduce this zeta parameter. So now given the vector zeta, which has a different value for each estimated value for each dimension, we're just going to scale the input by this estimated parameter for each dimension so that we can allow for different correlations. And now one quick change to the specification here, and the notation is just to reiterate that what goes into the mean function is not necessarily what has to go into the variance covariance estimation. Superscripting everything that goes into the mean function with tilde and everything that goes into the variance covariance estimation with this star. So important takeaway here is that the distance and dimensions have different correlations, and as they move closer together, the greater the correlation will be. As they move further away, the less the correlation will be in the prior. The dot product kernel is a non-stationary kernel, and I use this to model the outcome because my outcomes are very likely non-stationary. The spirit is similar to the Gaussian kernel or the separable exponential kernel in that the distance dictates the prior correlation. And the specification of the prior is a little bit more straightforward here. It's just omega is equal to this estimated term theta plus the dot product of the vectors, the input vectors. So the assumptions of the model, no spillover effects. So thinking about the West German GDP after German reunification, the idea of no spillover effects is, of course, that the reunification didn't affect the GDP of the other units in the study, which is an unfortunately strong assumption, but one that I have not been able to work around yet. There's also the assumption that no confounders exist that affect the outcome of other units. So we don't have some confounder that causes like a donor unit, to borrow from the synthetic control method terminology, like a donor unit in the analysis is not going to have some drastic increase in the outcome that's not explained by the variables of interest. But that said, GPP is much less sensitive to deviations from this assumption than the synthetic control method, which I'll talk about a little bit when I get into the application section. Importantly, this relaxes assumptions of conditional independence, linearity, homoscedasticity. So moving on to the first application, which is the replication of the original synthetic control method paper. So did reunification harm or improve West German GDP? The synthetic control method finds medium or long-term harm, which is likely due to the fact that the total integration of two differently operating markets is likely very difficult. But there's also reason to believe that it might improve GDP because the market size increased, right? The synthetic control method, which was originally used to test this, it's based on problematic linear modeling assumptions, sensitive to changes in outcome and donor units. It wastes data, which is related to the previous point on sensitivity to changes in outcome and donor units. By waste data, I mean it doesn't take into account all of the available data because it imposes a threshold on the weights that go into the creation and the estimation of the synthetic unit. GPP does not do that. And so this relates to the sensitivity because if one of those, I believe in the synthetic control method application, only 4 or 5 countries actually end up being part of the synthetic unit. And if one of those has a change in the outcome, it's going to drastically change the results. And probably most importantly, the synthetic control method does not allow traditional hypothesis testing. There's no estimate of uncertainty about the projected unit. So I'm going to control for the same as the original. Perhaps predictor is a better term for this because it's really just trying to increase the precision on the estimator by using predictors. So it's going to be inflation rate, industry share of value added, investment rate, schooling, and a measure of trade openness. And the donor units, again, borrowing from the synthetic control method terminology, are 16 OECD countries. And so these are the results of the GPP. The black line is the actual GDP of West Germany. The red solid line is the predicted GDP, and then the dashed red lines capture the 0.95 posterior. And what we can see is, well, this line is actually the predicted line is very, very similar to the synthetic control method, but we also see that the uncertainty about that prediction does not allow us to reject the null at conventional levels. So as I said, evidence suggests slower growth in the long or midterm and perhaps a demand boom in the short term. So if I go back, there's this little peak right after reunification that's arguably due to the demand boom. We cannot reject the null at conventional levels. And the synthetic control method does reject the null, but the hypothesis testing is very ad hoc. And the findings are insensitive to inclusion and exclusion of outliers. So Norway, for example, experienced an oil boom right around the same time as reunification. And so as I'll show you when I talk about the placebo tests, Norway had a higher growth in GDP than expected. But when I exclude Norway from the analysis, the posteriors remain almost completely unchanged, and the substantive conclusions remain unchanged. So the placebo tests, so first I drop the treated unit from the analysis entirely. So West Germany gets dropped. And then I analyze one country at a time as if treated at the same time as reunification. So this basically just means get rid of all of the post as if treated variables, both covariates and outcomes, and then analyze them as if they were treated. And then aggregate the results and check the noise level size. So we want to have that coverage at 0.95. So we might need to add noise or to take away noise in order to get proper coverage of 0.95. And with a psi in this application of 0.25, so all the variables are scaled before running the model and then rescaled back for the visual interpretation of the results. So psi of 0.25 is about a quarter of a standard deviation of the outcome, and we get a coverage of 0.95. And the placebos track the actual quite well. I'll show you this on the next slide. It's going to be a little bit hard to see, but you can see it's tracking, for most of these countries, it's tracking the actual outcome very well, and the coverage looks very promising. But if you zoom into Norway here, this is what I'm talking about, where the GDP grew higher than anticipated, but as I said, excluding it or including it does not really change the results. So GPP is arguably relatively insensitive to deviations of those assumptions I outlined before. So this novel application now, UK capital flight following the vote for Brexit. So the Brexit vote didn't implement any immediate policy change, but it did send a very strong signal to investors, right? And so one of the fears of the Brexit vote would be that there would be capital flight. And so I want to test this proposition. I expect there to be capital flight due to the signal of the Brexit vote. I'm going to measure capital flight by FDI outflows, foreign direct investment outflows. And then controls or predictors, just population, unemployment, and GDP. I could add more if you have any suggestions. I use all OECD countries in the analysis. And what we see here, again, black is the actual FDI flows, and red is the predicted FDI flows with the 0.95 reliable intervals. And we see that it's going, after the Brexit vote, it starts to go up, but not beyond in the first quarter after the vote. It doesn't go beyond conventional levels of reliability. Then in the second quarter, it peaks fairly high. And then it returns back down, but still stays higher than projected, just not at conventional levels. And what's, again, this sort of highlights the how we don't have to specify lags or leads or anything like that. We can actually look at the long-term, short-term effects by just looking at the graphical output of the posteriors and the actual data. So placebo coverage in this example is about 0.95 with a psi of 0.23. Shortly after the vote, FDI outflows increased as expected and remain higher than projected, but not at conventionally reliable levels. And I argue this will likely continue to be higher. And I am really interested to reapply this model in a couple of years, because I think GPP is perhaps uniquely suited to test these long-term effects of Brexit as it slowly rolls out, since it's not an immediate change, but they're sort of slowly rolling out some of these changes. So now moving on to generalizing the GPP, I generalize it in two ways. First, allow for multiple treated units at perhaps different times. And then the motivating example, as I already mentioned, is joining the EU and the effect on financial stability. Then I also generalized GPP to incorporate link functions so we can analyze discrete outcomes, which is often of interest to political scientists. And so my motivating example here is the negative binomial link modeling Afghan national terror attacks following the US intervention in Afghanistan. So multiple treated units at different times. GPP can be thought of as essentially an imputation task that's uniquely suited to deal with time series cross-sectional data, where it's actually taking into account those temporal trends, both within and across units. So basically, to allow for multiple treated units at different times, I simply get rid of any post-treatment controls and outcomes across all of the units at the time that they were treated. I then impute and then compare the outcome to the actual outcome. So the specification stays exactly the same as before. So the actual application that I use to motivate this is joining the EU in financial stability. So joining the EU offers many potential benefits, perhaps one of which is including financial stability. But transition may decrease stability in the short term due to the uncertainty in the transition. And so my expectation is that the short term will have a decrease in stability, but in the long term, we'll see an increase in stability. And GPP, nice feature of the model, once again, can test for these long and short-term effects. The data includes 61 countries from 1996 to 2017. This is just based on data availability for the data that I needed. 10 of these countries joined the EU in the time frame at different times. So the outcome is the banking Z-score, which captures financial stability. And then the controls or predictors are the learner index, which captures bank competitiveness within a country, which has been shown to affect financial stability, GDP growth, and real interest rate. And so if we look at the first 4 countries, I'll show all 10 countries. But if you look at the first 4, Cyprus, Czechia, Hungary, and Latvia, we don't really see much going on. It's not much, the projected unit is not much different from the actual outcome, and the reliable intervals bound the actual outcome across all countries. Moving on to Lithuania, Slovakia, Slovenia, and Bulgaria. We see much the same lack of evidence of an effect. And if we actually look at Slovakia and Bulgaria, they actually seem to have estimated opposite effects, where one hurt and one helped financial stability. And then finally, Romania and Croatia, where once again, we don't really see much going on. So there's not really much evidence of a treatment effect in this application. And there's certainly no evidence of a homogeneous treatment effect. There's no homogeneous patterns across these data. And so, yeah, it's possible that my expectations are incorrect because countries have to demonstrate that they're relatively stable before admittance to the EU. So maybe if they're not stable, then they would not be admitted to the EU. And just a note here about the placebos. I did the placebos one country at a time at, I believe, like 2004. So I pretended that they were treated in 2004, one country at a time. But it's really unclear if this is the best approach because the actual analysis involves 10 countries being treated at different times. So I would like to hear your opinions as to whether or not you think this is an appropriate way to approach this, or if perhaps maybe I should simulate, like randomly select 10 countries at a time and randomly give them different treatment times and then check the coverage. So moving on to link functions, using the negative binomial as an example. The specification is very similar. The code changes very, very little. I just modeled the mean in the same way, the latent mean, and then put it through a negative binomial link. The noise psi that I talked about before is added to the latent variable instead of the outcome variable, and then put through the link such that the projections all have are all on the support of the data, so they're discrete projections. And other links use the exact same process, but come with some other difficulties that I'll explain momentarily. So terror attacks by Afghan nationals following the U.S. war. The U.S. started this war in late 2001 with the explicit intention to reduce terror attacks. And I expect the exact opposite, particularly for this war. So war creates hostilities and opportunities for the spread of terrorism, but also this war in particular, with the intent to reduce terror attacks, I expect that it'll actually be a greater increase than just would be explained by them being in war. So the outcome is counts of incidents of terror from 1970 to 2018 across 188 nationalities. So I dropped a few very small countries like Barbados, simply due to lack of data availability, and I didn't think it would affect the results that much. But just to clarify this a little bit, the unit of observation is now an incident of terror from a national of a country. So it doesn't matter in this analysis where the attack occurred, but instead who committed the attack. And then the controls or predictors are war within a territory. So this is not imputed. So Afghanistan gets a 1 following 2001. And I do this to isolate the effect of this particular war, as opposed to just war in general. And then I also control for unemployment, spending on education, and ethnic fractionalization, all likely predictors of the amount of terrorist attacks by nationals. There's a lot of missingness in this data. So ethnic fractionalization is only estimated through 2015. Unemployment and spending on education has a lot of missingness in it. But this is not really a problem for GPP because the same way that we're basically imputing post-treatment covariates, it just naturally imputes all missing data. And all of that uncertainty will get carried over into the final outcome. So if we look, this is kind of hard to see due to the giant surge in terrorist attacks following the war. But so again, we have the number of attacks in black and predicted in red. Again, maybe I'll zoom in on this in my paper so that we can see the variation that's actually existing in those predictions. The predictions are ranging from about 3 to 5 with slightly larger, like 1 to 6 or so in the uncertainty estimates. And so I find that there's strong evidence in line with my expectations. The war had deleterious effects on terrorist attacks by Afghan nationals, and by deleterious, I mean the intention of the war was to reduce terrorism and seems to have had the opposite effect. And the effect seems relatively persistent. It spiked up and stayed pretty high. This is going to be worth revisiting after the war concludes, see if the effect lasts beyond treatment reversal or if it drops back down to normal levels. So the placebo tests for the negative binomial GPP are fairly straightforward because the outcome is an over-dispersed count. So we can just compare the placebos, how much of the terrorist attacks they're capturing versus how much they're not. And so with a noise of psi equal to 0.01, we get coverage of 0.95. But unfortunately, if we move to binary outcomes or a smaller range of support, like an ordered probit that doesn't have too many large observations, the coverage may be less straightforward to assess. We might not be able to just look at how many incidents are within the projected posterior. So for example, if we're predicting war, always predicting 0 would likely produce decent coverage. So I'm still working on how to perhaps deal with this, but of course we cannot test coverage of a latent variable since it's unobserved. So again, if there are any ideas out there, I would be more than happy to hear them. Future work, I want to more thoroughly examine noise levels for better suggestions. So again, for those times where the placebo tests, when the method is generalized, are a little bit less straightforward. Would like to be able to give better suggestions to practitioners. And additionally, the number of placebo tests that need to be done to establish that noise level could be prohibitively high in certain circumstances. I want to deal with treatment reversals, and I imagine doing this in a combination of 2 ways, which is just projecting further beyond, but that's going to add a lot of uncertainty. So projecting beyond treatment back into the time where there's a treatment reversal, and then combine that with considering a treatment reversal as a treatment itself and looking at what the treatment reversal does to the counterfactual. I want to test other link functions, and ideally deal with continuous treatment. So my thoughts on this are perhaps changing the treatment level to be 1 standard deviation above or 1 standard deviation below, and looking at the counterfactual and then getting a standardized estimate of what the treatment effect is. So the contributions, political science literature, it's similar in spirit to the synthetic control method, but importantly, with uncertainty, generalizes to multiple treated units at different times, supports link functions for discrete outcomes. In the GP literature, instead of projecting into the future, which it's typically used for, and projecting a counterfactual. Also, borrowing information from other units is not unique to GP, but it's not very common at all. And then something I've never seen before is this imputation of missing and post-treatment values, which make the model very, very useful. And then also GP is generally not used for substantive inferences, but this is an example in which we can use it for substantive inferences. So to conclude, GPP allows estimating a counterfactual with uncertainty, which allows for traditional hypothesis testing of an observational treatment effect, generalizes to multiple treatment units at different times and link functions. It's computationally expensive. Each run is not that bad, actually, ranging from 10 minutes to a couple of hours, but we need to find psi. So they need to run lots of placebo tests. And as of now, it's not an out-of-the-box method. You kind of need to know Stan to tweak it a little bit in order to get the model that you're looking for. But that said, I am working on developing an R package that will do a lot of this automatically. So with that, I thank you for your time, and I look forward to any comments and questions you may have.
Okay, thanks, David, for that presentation. At this point, David Carlson is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. And I'd like to start by asking about the comparison of this technique to the Abadi et al. Synthetic control method that I'm sure that most of us are aware of.
Yeah.
I noticed that you didn't show the results of that method compared to the GPP method in your graphs. Are there dramatic differences in the mean forecast?
No, there are not. So for the replication, where I replicate the analysis, the line is almost exactly the same. I should include the plots in the paper so that the comparisons can be made side by side. And then obviously with the generalizations, I can't really make the comparison because it doesn't apply to those applications.
One reason I was thinking about that was because generally speaking, the less parametric a method is, the lower the bias, but the higher the variance. And then also the trade-off between bias and variance can change, meaning you can get essentially a zero bias infinite variance estimator, which is completely unhelpful. Or you can get a finer trade-off, and it sort of depends on what approach you're using. And I noticed that, for example, in your projections of Germany pre and post unification, the confidence intervals were pretty wide, and yes. I'm kind of wondering, and substantively, it's pretty significant, and I'm wondering how much of that is driven by the fact that this is a quasi non-parametric. I mean, I know it is partially parametric, but it's a quasi nonlinear non-parametric method. And if we could do better in uncertainty by imposing some more assumptions.
So we could definitely decrease the uncertainty. So with that noise level that I talk about, so here's a plot of the projected, these are the placebo results without adding that noise.
Mm-hmm.
And they follow with much narrower uncertainty. And they still follow the data quite well, but the coverage is quite poor.
Right.
And so with this bias variance trade-off that you're speaking of, like that noise level is sort of meant to sort of adjust for where we might be making the trade-off where we shouldn't be, if that makes sense.
What I'm thinking about is it's possible to have appropriate coverage even with a partially biased estimator. It's also possible that two estimators can both have 95% coverage, but one is more efficient than the other. And
That's
so we can, what I'm really trying to figure out is not, can we turn down the uncertainty on this estimator because then the coverage just kind of becomes poor. But is there some alternative where we accept a little bit of bias, but we get more efficient coverage?
I mean, yes, that's a good idea. I should look into it more. Uh, yeah, I'm not sure if changing the specification or changing the priors or what might be able to accomplish that. I'd have to give this some thought.
A sort of related question. I've been thinking a lot recently, just for various reasons, about point nulls and rejecting them or failing to reject them. And in your case, in certain cases, like for example, if we want to argue that reunification with the East had no effect on West Germany's GDP, right? Let's suppose we want to say that. Um, Versus it had a positive effect or it had a negative effect. Um, it's actually pretty reasonable that we might actually not be able to accept any of those, right? We basically
Right.
might have to conclude this evidence is too uncertain, so we don't really know. And I'm wondering, like, because several times you say, like, oh, you can see we can't reject the null of no effect, which is, that's standard, that's a normal approach. But if I want to say, like, hey, reunification had no effect, I feel like I would want to say something where I was treating the null effect as though it was an alternative hypothesis, right?
Yeah.
I was treating that as something I was going to try to proactively demonstrate as opposed to assume. How would you adapt your method for that purpose?
Um, I haven't given that enough thought, to be honest. But I completely agree with you that I should give it more thought because, like, it was a little painful for me to say we can't reject the null hypothesis and all these things because, I mean, there was evidence, and you know, that's, but that's sort of, I digress. Um,
Right, I understand what you're saying.
uh, but but yeah, I should give some more thought as to how one could test, uh, basically flip the null and the alternative hypothesis, and look at how maybe we could do a more thorough investigation as to whether or not there actually is a null effect.
Yeah, I mean the whole framework of Neyman Rubin hypothesis testing leads us away from that, but because it always has a null space and an alternative space. But I'm starting to think that it might be more appropriate for us to be able to conclude we don't know, or in other words, like to be able to say like, here's the range of reasonable possibilities, um, and that's all we can tell you. Which is not quite a 95% CI, right? Because
Right.
nulls you can't reject are not the same, not exactly the same thing. Um, well, anyway, now I'm digressing. Um, there was one other thing I wanted to. Oh yeah, so you're applying this method specifically to time series data, and there's been a lot of interest recently in modeling time series data, and in particular, the degree to which we need to watch out for non-stationarity or co-integration among the series. And there have been some examples. You can see whenever a lag-dependent variable is near 1, that kind of makes you nervous that whatever is about to follow is not, may not be good. And I'm wondering, you mentioned that you don't have to worry about lags and leads when you're taking this approach. And essentially, my question is, why don't we have to worry about stationarity or non-stationarity, the unit root, if we're taking this approach?
Well, so specifically with the outcome measure, the variance covariance estimation is a non-stationary kernel, which will basically allow for it takes into account the temporal trends but in a non-stationary approach. So you might have to adjust even the explanatory variable to have a non-stationary modeling strategy if you think that you have to worry about non-stationarity in that. Mm-hmm. But in previous research, I've found that like dynamic models where you include lags and leads tend to really, well, it biases estimates, but I guess the purpose of this project isn't really to get substantive estimates of like parameter estimates exactly. Yeah. So I should say I have played around with including a lagged dependent variable with decent results, but this approach seems to be better. But I haven't really looked into it systematically in a and maybe combining the two would also be a good idea, but I could look into this more systematically and see maybe which modeling approach is more conducive to the goals here.
All right. Well, at this point, I'm going to thank David for being our presenter this week. I'm going to note that his presentation will be posted to our website shortly after this broadcast if you'd like to share it with a colleague or watch again later. I'd also like to advertise after spring break on Friday, March 20th, we will host a talk by Jeff Gill from American University. Please check out our website, www.methods-colloquium.com, to get more information about this talk. So, David, thanks for being here.
Yeah, thank you very much.
And see everyone after spring break.